When we talk about water, stereotypical images often come to mind. A high-altitude spring, waves crashing on the shore. But discussing water from the perspective of the environmental engineering requires moving away from these stereotypes. In this lesson, we will discuss the relationship between water quality and usage requirements, which determine the treatment processes needed to make the supplied water suitable for its specific use. Water in the environment can have various sources and, as a result, different qualitative characteristics, commonly referred to as compositions. Each use has specific requirements, meaning it needs specific compositions that must be met in order to avoid causing harm. For example, drinking water is not necessary for irrigation or street cleaning, and it is not even suitable for pharmaceutical processes. The use of water for drinking is regulated by law, while other uses are guided by. Technical reference documents are relied upon. Whenever the characteristics of the supplied water do not meet the requirements for its intended use, a series of treatment processes must be applied, each designed to remove a specific substance. What defines the quality of water? It is defined by a set of physical, chemical, and microbiological parameters that identify the physical form in which a substance is found, its chemical origin, and the presence of organisms. We talk about substances rather than contaminants because a substance is only considered a contaminant when it compromises the use of the water resource for a specific purpose. For example, salts, including calcium, are necessary for drinking water. But they pose a problem in sectors such as microelectronics and textile finishing, where water with different characteristics is required. In the latter case, we can therefore consider them contaminants. We can source water from groundwater, aquifers and springs water, from surface water like rivers or lakes, and from saline water. Groundwater generally has some typical characteristics. It is low in suspended material, has a good level of mineralization, meaning dissolved salts, and depending on the specific geology, may contain substances that can limit its use for human or industrial purposes. It is susceptible to chemical and microbiological contamination, depending on the specific local context. River waters, on the other hand, has highly variable characteristics, influenced by the hydrological regime, and is more strongly affected by the impacts of climate change, not just in terms of quantity but also quality. It typically contains a significant amount of suspended solids and naturally occurring organic matter, and is susceptible to both chemical and microbiological contamination. Lake water is similar to river waters, but its variability is influenced by natural mixing processes and its trophic state. Furthermore, due to their high dilution capacity, chemical contamination in lakes is often difficult to detect, especially in the case of emerging contaminants, whose toxicity can become evident even at extremely low concentrations, on the order of just a few nanograms per liter. Finally, saline waters, whether surface and groundwater, tend to have fairly stable characteristics, but have historically been less exploited due to their high salt content. Reducing that salt content poses a greater technological challenge than many other aspects of water treatment. That is why groundwater is the most widely used source. Its relatively stable quality over time makes it easier to define and manage treatment processes. To provide water that is fit for purpose, it is essential to consider 5 key criteria. The first criterion involves identifying the target contaminants, that is, understanding the characteristics of both the supplied water and the water required by the end users. By comparing the two, we can pinpoint which contaminants need to be removed, the target contaminants, and select the most suitable removal processes. At this stage, we must also keep in mind the impact of climate change, which affects not only the quantity but also the quality of fresh water sources, as we have previously discussed. The second criterion involves defining the treatment sequence based on a principle of resilience, which is applied through the multi-barrier approach. This means setting up multiple treatment processes in sequence, all working towards the same removal goal. In doing so, we ensure greater reliability of water quality, even in the event of significant or unexpected changes in the characteristics of the source water or in case of system malfunctions. Interaction with the distribution network defines the third criterion, which should not be overlooked. Water must be delivered to the point of use while maintaining its quality. During transport, regardless of the size or complexity of the network, reactions can occur that alter the chemical and microbiological quality of the water. The quality of the water before the network must also be assessed so that specific treatments can be applied if needed to ensure its balance. The fourth criterion concerns the service life of the treatment plant. The removal processes and their sequence must meet user requirements and adapt to regulatory changes anticipated over the treatment plant's lifetime. In the case of drinking water treatment, this means several decades, while for industrial plants, the time frame is closely tied to production and market dynamics. Finally, investment and operating costs make up the last criterion. Once the previous criteria are met, the chosen treatment sequence is the one with the lowest cost per cubic meter of water. Removal processes, referred to as operation units, are classified based on the principle used to remove target contaminants, which can be physical, chemical, or biological. Treatment sequences vary widely due to many possible combinations arising from the first criterion. To support the selection of operational units, there are descriptors of the molecular characteristics and the physical-chemical properties of the target contaminants, which allow for an initial screening of applicable operation units. This is followed by the identification of the most appropriate ones based on the concentration of the target contaminant and the concentration of other substances present that may interfere. In conclusion, from an engineering perspective, it is possible to produce water suitable for any given use starting from any type of water. It is simply a matter of carefully choosing the most appropriate operation units and arranging them in the proper sequence, as well as overcoming any preconceived notions.